Okay, our next speaker is Laurent Drissen from University of Laval. Yes, talking about Wolf-Rayet with SITELLE. Please take it.
So in the background, the image you see in the background is about 15% of the field of view in M33 from signals. And thanks to Sébastien for introducing the subject. You see a lot of ionized gas here, diffuse ionized gas, but you also see giant H2 regions, NGC 595, 604 right here. The bubbles, the blue bubbles here are supernova remnants, and you even see some lots of planetary nebula. But I will talk about Wolf-Rayet nebula in this talk. So I would like to acknowledge my collaborators, and we have two parts in this project. One part which centers on the Milky Way, Wolf-Rayet nebula, and a part that studies, in general, the population of Wolf-Rayet nebula in local group galaxies using signals. So what you notice on the upper part of the HR diagram, the mass loss is really ubiquitous. You see it everywhere, and most of the stars above 20 solar masses loses about 20% to about 50% of their mass before exploding as core collapse supernova. And this is obvious when you look at the IUE spectra, ultraviolet spectra of these stars. I concentrate on Wolf-Rayet stars. They are the most beautiful ones. They are characterized by very broad, intense emission lines that actually show that their mass loss is extremely large, 10 to the minus 5 solar masses per year on average. Terminal velocities of a few thousand kilometers per second. And you have essentially two classes, the nitrogen, the WN class, and the WC class. So essentially you see helium and nitrogen lines here, and carbon, oxygen lines, and a few helium. Only a few of them show hydrogen, but most of them do not show the presence of any single atom of hydrogen in their spectrum. So here you have an evolutionary diagram that shows the evolution of a star, 60 solar mass star, from the center to the surface as a function of time. And you see that the star loses already in the main sequence. It loses a lot of mass in the main sequence. Then there is an extreme event that we call the luminous blue variable, in which the star loses a lot of mass. And then once most of the hydrogen envelope has been expelled, it reaches the WN phase, where you see the products essentially of the CNO cycle, helium and nitrogen. The star loses mass again, and we are now at about 25 solar mass stars, solar masses here, and it reaches the WC sequence, where you see the product of the triple alpha cycle, essentially carbon and oxygen. And then the star will eventually explode. We haven't seen any clear sign of Wolf-Rayet star exploding, but this is our hope. So it means that the star loses more than half of its mass before exploding. So this mass is supposed to go to the surroundings, and the star is very hot, so you're supposed to see an ionized nebula around every single Wolf-Rayet star, but this is not the case. This is exemplified by this picture I took in my backyard, just with a camera, absolutely no telescope involved, just a very narrow H-alpha filter. In the Cygnus region, you see about 9 Wolf-Rayet stars. Only 2 of them show an obvious Wolf-Rayet nebula around them. So 22% of Wolf-Rayet stars in the Cygnus region in the Milky Way are surrounded by a nebula. So I will just go through a few examples of the stars that we have observed with SITELLE at the CFHT. This is NGC 6888, one of the Cygnus Wolf-Rayet nebula. This is a Doppler map, and I will just flash some results because we have many. So the colors here represent the velocity at which filaments are moving. So the blue here are approaching us, and the red filaments are moving out. And what we see is that the velocity, the ejection velocity, is around plus or minus 60 kilometers per second in this case. Another example, NGC 2359, the Wolf-Rayet star is right here. It's another Doppler map, so the expansion velocity is more or less the same, more or less as 100 kilometers per second. But I want to highlight the fact that this is a molecular cloud, And we really see the impact of the hot Wolf-Rayet star here on the molecular cloud itself. If you just join the parts, go back and forth, you see that the molecular cloud is being photodissociated by the light from the Wolf-Rayet star. And this is the last example, our last tiger, WR134. This is a very recent data, so this is just a Doppler map showing the complexity of the matter being expelled by the star. So now we go to the signal sample. We have a few local group galaxies in the signal sample. M33 is right here, M31, and a few dwarf galaxies. Most of them do harbor Wolf-Rayet stars. For example, M33, there are 211 known Wolf-Rayet stars in this galaxy. The sample is essentially complete because these stars are very bright. It's very easy to get them. In the signal fields, we have 85% of them. And this is an example of one of the fields. The Wolf-Rayet nebula are highlighted. We'll get rid of the stars. So the only thing you see here are the nebulae. And you see that they are here and there. They pop up here and there. So they're not that frequent, but still a galaxy without Wolf-Rayet nebula would not really be a good, interesting galaxy. So we found 33 Wolf-Rayet nebula among the 178 known Wolf-Rayet stars. So this is just a sample of them. The smallest one has a diameter of about 4 parsecs. It's just very resolved. The most complex is here. We even have a bipolar nebula, and I will just show you one example. This one, which is quite complex. The central part, this is a color-coded image. The blue represents oxygen 3, and the red, orange represents H-alpha. So here you see that the Wolf-Rayet nebula stands out. The diameter is about 14 parsecs for the inner part. And we have lots of lines ratio, and the presence of the Wolf-Rayet star is really obvious here when you look at the oxygen 3 over oxygen 2 map. Same thing in the oxygen 3 over H beta map. And we also have, as Sébastien mentioned, we also have the velocity and the velocity dispersion with very high precision. And we see the impact of the Wolf-Rayet star here and on the velocity dispersion. So it's more or less the cases that I showed before for the Milky Way. We see the velocity expansion, and we see it also in the Wolf-Rayet nebulae. So this is our interpretation of this kind of ring nebula. We have the small one, which is essentially due to the Wolf-Rayet wind and Wolf-Rayet ionization UV flux here. This is perhaps the shell that was created during the O phase. And this larger shell probably is a supershell coming from all, well, there are not so many, but there are a few of them, massive stars here, but the velocity dispersion, again, is visible here. So as a summary for this galaxy, 33 nebula are found around the Wolf-Rayet stars. So it's only 19% of the sample that shows obvious signs, and we should look for them. And only 19% show an obvious nebula associated with them. And there is absolutely no clear correlation between the spectral type, WN or WEC. Why not 100%? So there is one hypothesis, is simply dilution. As a function of time, the nebula will expand. At some point, the emission measure will go below the detection limit. This is a possibility, but in M33, it's not that obvious because, as I mentioned, there is no clear evidence for a correlation with the evolutionary type of the star. So it's still work in progress. We still don't understand why 80% of the Wolf-Rayet stars are not surrounded by an obvious nebula. M31, we have a few fields in signals. In the center, it's really nice. You see the gas spiraling into the central black hole, but I'm not interested in black holes. So we go to Wolf-Rayet. Well, eventually, all Wolf-Rayet stars are supposed to become a black hole, but not a black hole like the one in M31. So we have 29 stars in the signals field. Only 7 of them are surrounded by an obvious Wolf-Rayet nebula. Again, it's more or less the same ratio, 24%. This is the Wolf-Rayet Nebula I really prefer. In this field, there are only 2 of them, and this one is really a nice one. The Wolf-Rayet star is here. You see a clear round nebula with possible structure right here. This is actually an interesting case. We have an image with HST. The F475W includes H-beta and oxygen-3, so we can compare the results here. And we got very good news a few days ago. SITELLE is the next target. It's also a local group, dwarf galaxy. It harbors about 30 Wolf-Rayet stars. It's really unique. It was not included in the original signal sample because the absorption is relatively large. So we couldn't do all the science for signals, but in the case of Wolf-Rayet Nebula, in H-alpha and even in oxygen-3 and even in oxygen-2, it will not be a big problem. So this is the next target for our survey. But since we learned that SITELLE will retire, it will take just a few seconds or a few minutes, if I'm allowed to thank first the people of Hawaii for accepting SITELLE, and of course the CFHT as an organization. It has been a real privilege to have SITELLE installed at the telescope. But I would like to thank also the staff. The CFHT staff is incredible. And I know that Greg is here, Kevin is there. And I hope that Manbari would be here because he also has been involved in SITELLE a lot. So a big mahalo nui loa to all the staff at CFHT. Thank you.
Thank you. And we'll start taking questions. We'll start here.
Beautiful results. I was wondering whether there was any correlation or anti-correlation between the presence of the bubbles and the binarity of the Wolf-Rayet star?
Actually, we don't know if the stars in the signal sample are binaries at all. In the Milky Way, it's not obvious, and it's really difficult to assess the binarity of the Wolf-Rayet stars in the signal sample.
Okay. Any other question?
Yeah, beautiful data. Is it just maybe a matter of perspective, but it looked like the stars were not necessarily at the center of the nebulae. There seemed to be some asymmetry. Is that just a visual impression, or it's actually the case?
In some cases, essentially, it's not the case. It's either because the mass loss itself was not spherically symmetric, or the fact that the interstellar medium around it was not spherically symmetrically distributed. Because what you see is the wind pushing, in some cases, pushing the interstellar medium. And if you just don't have interstellar medium on one side, so in most cases, the star is not exactly in the middle.
Super.
Great. I think for the sake of time, we'll stop here, but let's thank our speaker again.